Okay, have you ever actually stopped to wonder how systems like ChatGPT pull off what they do? I mean, they answer complex questions, they write detailed essays, generate code, and hold conversations with us like it's totally natural. Well, today we are diving into this explainer to completely demystify the secret engine behind all of it.
You've definitely used these tools, right? You type in a prompt, hit enter, and watch in awe as text just instantly materializes on your screen. But here is the crazy part. How on earth did machines, which literally only understand ones and zeros, learn to speak human so naturally? The secret behind all of this is something called a large language model.
So here is our roadmap for today. Number 1, what exactly are LLMs? 2, the anatomy of language. 3, the revolutionary transformer architecture. 4, training the AI brain. And finally, number 5, LLMs in the real world. Let's get into it.
Starting with Section 1, what are LLMs? Let's look at the big picture.
Think of this like a set of nesting dolls. Artificial intelligence is the biggest doll, the broad concept of machines imitating human intelligence. Inside that, you have machine learning, where systems learn from experience. And nestled entirely inside that is deep learning, which uses complex neural networks. Large language models? They live right there in that deepest, most advanced deep learning layer.
At its core, a large language model is basically a highly advanced pattern recognition and text prediction system. If you want a really simple analogy, think of it as a super-powered version of the predictive text on your smartphone. You type, "the sky is," and it calculates the statistical probability that the next word is blue. But instead of just guessing one word based on your recent text messages, it's predicting massive, complex sequences based on literally billions of documents it has read.
Moving on to Section 2, the anatomy of language and its building blocks.
This is a pretty fascinating truth. AI actually doesn't read full words the way you and I do. Instead, it uses a preprocessor to chop text up into tiny little pieces called tokens. So a giant word like anti-disestablishmentarianism, yeah, try saying that 3 times fast, isn't processed as one big unit. It gets sliced into 6 distinct subword puzzle pieces: anti, dis, establish, ment, Arianism.
These tokens are absolutely the atomic unit of how AI models language. Just to put that into perspective, in English, one token is usually about 4 characters long. So if you have 400 tokens, that's roughly 300 words. By chopping our messy, complicated language into these tiny pieces, the AI can assign a unique integer identifier to every single token. It's basically translating human language into pure, calculable math.
Now here's where it gets really mind-bending. How does the AI actually get meaning out of those numbers? Well, those tokens are transformed into what we call embeddings. You can think of them as coordinates in a massive multidimensional mathematical space. The machine figures out mathematically that the concepts for dog and puppy are physically clustered close together in this space, while dog and computer are placed miles apart. It is literally mapping the meaning of our words into geometry.
All right, Section 3, the transformer architecture, or as I like to call it, the powerful engine. This all tracks back to a legendary 2017 paper called "Attention is All You Need." And honestly, this architecture changed AI forever. See, before transformers came along, AI had to read text sequentially, word by word by word. It was slow, and the AI would constantly forget the earlier context of a sentence. But the transformer uses these foundational encoder and decoder stacks to process all the tokens simultaneously, in parallel. It completely revolutionized the speed and scale of what artificial intelligence could do.
And the absolute secret sauce of that architecture? The attention mechanism. Imagine it acting like a highly accurate matchmaking service for words. When the AI reads the sentence, the animal didn't cross the road because it was tired. How does it know if the word "it" means the animal or the road? Well, the attention mechanism uses query and key vectors, basically comparing 2 characteristic checklists to figure out exactly which words relate to each other. It keeps the context crystal clear.
Okay, let's jump to Section 4, training the AI brain and the learning process.
Training happens in a massive, rigorous loop. Step 1 is data collection. We are talking about gathering billions of documents, books, and websites. Step 2 is learning patterns. This is where the model basically plays the biggest game of fill-in-the-blank ever, predicting missing words and adjusting its math when it guesses wrong to learn grammar. Step 3 is fine-tuning, where we specialize the model to actually be useful, like for coding or medical research. And finally, Step 4 is rigorous evaluation and testing.
As the model churns through all that data, it develops what we call parameters. You can think of parameters as the learned internal memory connections inside the AI's brain. And get this, 1.8 trillion. That's 1.8 trillion with a T. That is the estimated number of parameters inside modern models like GPT-4. It's the sheer, unbelievable scale of these connections that give these models their seemingly magical capabilities.
But, as you might guess, raw, unsupervised intelligence can be a little chaotic or even hallucinate false information. To prevent the AI from generating harmful or just total nonsense text, engineers use RLHF, reinforcement learning from human feedback. This acts as a crucial guardrail. It adjusts those trillion parameters based on actual human scoring to make sure the AI's responses are safe, helpful, and actually accurate for us to use in the real world.
Which brings us to our final part, Section 5, LLMs in the real world and their applications.
Because these modern LLMs can handle such incredible nuance and keep track of massive context windows, they are definitely not just toys. They are deployed across major industries right now. They're instantly summarizing 90-minute corporate sales calls, extracting exactly what needs to be done from messy customer support tickets, writing actual production-ready software code, and even powering autonomous voice agents that sound completely human. It's wild.
But let's take a breath and ground the hype for a second. As incredible as they are, the AI does not have a conscious brain. It doesn't actually know what it's saying the way you and I do. As this highlights, it is simply calculating mathematical probabilities across its trillion parameters at lightning speed. It's a beautifully complex, highly sophisticated statistical engine.
It's a fascinating structural illusion of intelligence. And honestly, it leaves us with a really profound question to ponder. As these models keep scaling up to trillions of parameters, and their memory windows grow even larger, what invisible patterns in our human language are they going to predict next? What limits are these massive prediction engines going to shatter in the next few years? Thank you so much for joining me for this explainer, and remember to keep questioning the technology around you.